Hello everyone. In this video, we are going to use Jamovi in order to help us do a regression analysis. Now let's look at our scenario. It says Megan is working with NASA to monitor a rover that has recently landed on Mars. Her job is to track the weather to determine when they should deploy shields over the rover's sensors. Unfortunately, if she puts up the shields, they are unable to perform the mission experiments, but if she leaves them down during intense dust storms, the sensors will be permanently damaged. Her main concern is about the amount of particles in the atmosphere during the dust storms. Instead of sitting up all the time with her fingers hovering over the Shield Now button, it would be too late anyways to protect the sensors due to the time it would take to send the signal. She thought it would be way better just to set up an algorithm to tell the rover when to shut down itself. Measuring wind speed is one of the few sensors that is always safe to have running. As such, she wants to be able to predict the amount of particulates in the air based on wind speed. Josie starts taking measurements and wants to see if there's a relationship between airspeed and the number of particulates in the air. She tested the significance level of 0.6. Okay, so let's go ahead and look at our data. We have the number of particulates, so this is in per cubic centimeter and kilometers per hour. So let's go ahead and just copy this data and let's bring it over to Jamovi. Let's paste that in. And let's rename A as like particles and B, rename wind speed. Okay, so what type of data are we dealing with here? All right, so in this one, notice how we have numerical in both columns. So we're dealing with numerical by numerical. We're not looking at different groups, but we are trying to measure one piece of data and predict another piece of data. And instead of using the categories to predict what's going on, now we're going to be using numbers to predict what's going on. So the predictor variable of interest is going to be our wind speed because that's like easy to measure. And a response variable, what we want to be able to predict is actually like the particulates in the air. So the population of interest is going to be like this atmospheric conditions near the rover. That's like what we're measuring. And then the parameter of interest is the true mean particles per, or particulates per cubic centimeter. Okay, when we do our regression analysis, the big thing that we need to check isn't really like a sample size or anything, but it has to do with our residuals. We're looking for normality, independence, that it's centered about zero, that we've got linearity, and that we have constant variance. So if we have issues, we need to check on them. So this is a QQ plot, but I also want to show you how you can, or not a QQ plot, excuse me. This is a residual plot, but I want to show you how you can also get it inside of Jamovi itself. So now that we have our two columns, we can go ahead and click on regression. And we want to do a linear regression. Okay, so our dependent variable is what we are actually interested in, as we've said kind of up here in the response variable. It's also known as our dependent variable. So we're going to go ahead and put our particulates there. And then where we put our predictor is actually where we put in. Okay, so what we're going to go do is we're going to look at our assumptions checks right here. And we're going to go grab residual plots. Okay, let's go ahead and take a look at what we have. So here is our residual plot. And there's a couple others. So we have the fitted, we have the particulates, we have the wind speed. We're going to look at the fitted one. We're going to just ignore these other two and just look at this fitted residuals. Okay, so that's how you can get it in Jamovi. And over here, my open math has already provided it for you. And so we need to look to see if we have any problems with any of this stuff. So we can look for normality. Normality is kind of a hard one to see here because what you want to see are like the data points clustered about this center line, and as they go further and further away, that they get less and less common. So you can kind of see that here. I think it's way easier to just look at a QQ plot of these residuals. So we can just click on the QQ plot, and over here, when we click on the QQ plot, we interpret this exactly the same as we looked at ANOVA. It's like, as long as these data points are landing pretty much on this line, we can then say that, hey, we do not have a problem of normality with our. So that's how I would answer the normality one. It's much easier to see in the QQ. Okay, next one is independence. And the problem with independence is when we see like a ton of clusters all over the place. And here we don't see any clusters. You're always going to see like a few data points like bunched up together. But what would be bad is if you saw like a ton of points up here and then a ton of points over here and then a ton of points over here with a whole bunch of empty space. So it looks like we don't have any problems with independence. Centered about 0, if we come over and we look at this residual plot here, we have this 0 line going straight through the middle. And how these programs build these residual plots is they center them about 0. So unless if there's like a massive problem, this one you almost never have an issue. Okay, linearity has to do with, do we see like some weird squiggle pattern, or is there like some parabola? We want it to look like this amorphous cloud of like no pattern really at all, and so we don't have a problem with linearity. Finally, we're looking for, is there constant variance? And we look for that by see if there's fanning, like we'll see this kind of sideways V or like a greater than or less than shape. Or we'll kind of see this starting small, go big, and then come back down. Or you could also see it kind of an hourglass shape. But it's basically like if you see any pattern where the data is getting more and more spread out is bad. Anyhow, so in this one, this actually looks really good. So it looks like that we have issues with none of these. All right, so the method that we should be using for this analysis is going to be regression. And then the distribution that we should be using here is we're going to be using an f-test again. Okay, so now let's go ahead and establish what our hypotheses are. And remember, when we are doing ANOVA testing, we are basically saying, like, is there a slope or is there not a slope in our data? And the baseline assumption is that there is no slope, or that beta 1, no slope going on. And now, if there is a slope, that means that there is a relationship between wind speed and the number of particulates. And so I'm going to say that it is not equal to 0. Now, you can do one-tailed tests in regression, but it's a little more rare. And so this is just how we do it with not equals. Okay, next thing, let's go ahead and build a scatter plot. So scatter plots are actually pretty easy. In your exploration, there should be an option that says scatter plot. You might need to install a package or a module that's called scatter. I think if you go to modules and you look at the Jamoke library, go ahead and scroll on down. I think scatter is an add-on that you can put on. Just a second. It's not. Oh, there it is. Yep, it was the very first one. Scatter. It gives you a couple of other options. So if this is not installed, go ahead and install it. But let's go ahead and go to our explorations scatter plot. And our x-axis is going to be our wind speed. Our y-axis is going to be our particulates. And let's go ahead and include our regression line, our linear regression line. And this is kind of what we are trying to get the equation for. And is this a significant line or is it a insignificant relationship? And it looks like we've got a pretty good relationship. Okay, so if we were matching this up to this data over here, it's just asking you to pick out which plot actually represents the data. The relationship that we have here is a positive relationship because it starts as the x increases in value, the y increases in value. All right, so let's go ahead and look at our alpha level, and it says that, okay, we want to do a significance testing of 0.06, so that's totally fine. We can go down here and type in our alpha level of 0.06. Excellent. And now we want to know what B0 and B1. So these are the estimates that we have of our line in order to actually build this line over here. What are our statistics that we get in order to make this line? Okay, we are actually ready to go back and look at our linear regression results because we can actually track those down from here. So the estimate that we have for these is actually the intercept is what we have as B0, and B1 is the estimate for the wind speed. So if we click on here, we have 11.89 and we have 0.58203. And those are our estimates here. Now we also have our r squared and our f statistic. And if we click on our r squared, we get 0.5146, 0.5146. Now the r squared tells us what percentage of the variability in the data was explained by the model, or like how well does the model predict what's going on. So we don't have a ton of predictability. This r squared is actually pretty poor. But let's also grab our f statistic. If we want this f statistic, we need to go ahead and grab a little bit extra stuff. So if we go down to the model coefficients, we actually want a ANOVA test as well. ANOVA test and actually regression testing is actually very, very similar, but this is how we get our F statistic that we're wanting. We want this this 38.166, and that gives us our F statistic and our p-value as well, which is like much less than 0.5. It's very, very small, and we get that our p-value is less than our alpha. Okay, at this point, we want our confidence interval. And, handy dandy, our Jamovi can actually give that for us. We want a confidence interval, but we need to get it at the right level because we said that we had an alpha level of 0.6, so we need an interval of 94%. And when we do that, give it a moment to think, it will provide both a confidence interval for the intercept and a confidence interval for the slope. Now, we actually are not interested in the confidence interval of the intercept. We're really not interested in the intercept at all. A lot of times the intercept is really far outside of the range of data that we're dealing with. We have to remember that our regression model is really only good, let's see, over the range of data for which we caught. So we only caught wind speeds from like 20 kilometers per hour to maybe 60 kilometers per hour. And 0 kilometers per hour is like way over here. And we're not interested in it. Maybe we have a totally different pattern of what's going on. Okay, so the confidence interval for beta 1 is we think that the true slope or the true relationship, back up here, is somewhere between a slope of 0.399 and 0.764. And that gives us our confidence interval. And our decision should be still to reject the null. Okay, so now when we are rejecting the null here, we actually have a bunch of things that we need to do because we need to not only, say that we have sufficient evidence and give the F statistics and talk about our null hypothesis, we also need to incorporate in our R squared, and we need to talk about kind of the slope, and we do that as we're talking about our confidence interval. So let's go ahead and look at this conclusion. So it says that we have collected sufficient evidence and says F136. How do we get that? Well, if we come back over here, we have this F statistic here. We have 1 degree of freedom and 36 degrees. So that's where those come from. F136, and we then put in our F statistic, report our p-value and report our alpha. Oops, sorry, we're going to look at this one. To reject the claim that there is no relationship between the wind speed and the number of particulates in the air, and instead claim that there is a relationship between the two. Okay, so we rejected our null hypothesis, and we are claiming the alternative. We then are saying that our model was able to account for 51.4604% of the variability in the data, which is a poor model here. And then it says that we are 94% confident that for every 1 kilometer per hour increase in the wind speed, the true mean number of particulates per cubic centimeter increases by somewhere between 0.3991 and 0.765 particulates per cubic centimeter. Anyhow, so that's how you go ahead and you go through and you are able to use Jamovi in order to run a good regression analysis. Now, what's interesting here is I want to look at this scatter plot so that you can understand what it means we have significant results, but a pretty poor model. So what's going on is it's saying that yes, wind speed does affect how many particulates are in the air, and we can very clearly see that there is this relationship. But there's also a bunch of other variables that are going on, and that's why we see that there is so much more variability in this data. So we do account for some variability in the data from this wind speed, but we do not account for all of it. Now, if you saw a model that had a very high R squared value, these data points would be very, very closely clustered about this regression line. Anyhow, that's how we do it in Jamovi, and I hope that you have good luck on doing regression analysis on your own.